back, everyone, to continuity one-sided limits today. In the next hour or so, you'll determine how continuity at a point and continuity on an open interval both work. You'll understand it. You'll understand how one-sided limits and continuity on a closed interval operates. You'll be able to use the properties of continuity, understand, and use the intermediate value theorem. You got it? Pretty much one-sided limits is the key. Continuity was what we'll start with. First thing you need to know, continuity at a point and on an open interval. What does the word continuous mean? When I point to you, you yell out what you think it means. It means unbroken or uninterrupted. So, a continuous line is a line that if you had a piece of paper and you took a pen to it, you would draw the line on that paper or pen with the pencil or pen, right? And you would never lift that pen or pencil up. You just keep on drawing the line. That's pretty much what continuous means. So there's three things that have to be true. There's always rules, and if these rules are followed, you have a continuous line. Open interval pretty much means it goes from negative infinity to infinity. So it just keeps on going forever. So first rule is f of c is defined. That means when I say like f of 3 equals 1. You actually have a value at the point. Step 2. So that's no holes. So you can't have any holes. And you can't have any asymptotes. So if there's a hole or an asymptote somewhere in this, right, at the point that you're looking at, if that's a hole or an asymptote, not continuous. Step 2. The limit f of x exists, as x approaches c. So that means there's actually, say we're still doing at 3, there's still a limit at that point. Now, in order for there to be a limit, that means the left side approaching this point has to be approaching from the right side as well. It means just the left and the right both approach the same number. If they approach the same number, you do have a limit. Also, it can't be unbounded behavior, can't be oscillating, can't be not there. All right, number 3. The limit of f of x as x approaches c has to equal, this limit right here has to equal your actual value, f of c. That means the hole has to be filled in here. All right? And that's pretty much it. So what I want you guys to do now is look at problems 1, 2, 3. Try them real quick. Say if they are continuous or not continuous. And if they're not continuous, why? All right, let's move on. First one is not continuous. Oh, why are the graphs not continuous? They're all not continuous. The reason it is f of c is not defined. So this really is not an open interval. This is just an interval from a to b. But at c, right, why is it not continuous? Because there's a hole there. Okay? Because there's a hole there, f of c is undefined. Here, y at c, is this not continuous? Which one of these rules? The limit doesn't exist. The limit from the left is different than the limit from the right. And finally, part 3. Why isn't this one? Well, this is rule 3. The actual value at c is different than the limit. There is a limit here because from the left and the right approaches this hole right here. But because this hole and this actual value at c are different numbers, it's not continuous. You would have to actually take this and plug in the hole. Got it? Awesome. That's continuity. That's pretty easy, right? So really quick, 1, 2, 3, and 4. Are they continuous? If not, where are they discontinuous? Ready? Look at the graph. Not continuous. No. Where is it not discontinuous? Well, we're about right here. That's an asymptote, and that asymptote is at x equals 0. Okay, you always talk about discontinuity or continuity regarding the x-axis. So it only is where does this graph not continuous on the x-axis, the horizontal. Let's look at this one. Is this continuous? No, not is continuous as well. Oh, sorry. And the f of 0 is undefined because of the asymptote. This one, not continuous. Why? Boom, right there. Because what is that? That is a hole. Okay, so at x equals 1, there's a hole, right? So f of 1 is undefined. It has to be defined. It actually has to be a number. Because it's a hole, it's undefined. Right? What about number 3? Is that continuous? Yes, it is continuous. Now look at what happens here. This is a piecewise equation. Oops, sorry. Even though it goes up and then it continues to go up, the graph remains unbroken and it continues. What about the sine curve? This arrow should be headed back this way. It's a weird looking arrow. Is that continuous? it is indeed continuous. It just keeps on oscillating and continuing on forever. Got it? Now, it's not the super oscillation one, the one where it's really close. This is just a regular a period oscillation, which is okay. All right, let's look at problems 5, 6, 7, and 8. Is the limit continuous at C? Explain why or not. Go again. All right, for 5. Is it continuous? No. Why not? Well, even though the limit at 3 is 0, right? The actual value at 3 is 1. They're not equal. That's why it's not continuous. All right, what about 6? Is that continuous? That is not continuous as well. So 1 is not equal to 0. Okay? That is not continuous. The reason for it is, same reason over here. F of negative 3, the actual limit here, does not equal the point. The limit is at 3, negative 3, 3, negative 3, 4. All right? The actual f of negative 3 is 4. The limit here is 3. 4 does not equal 3, so it is not continuous. They would have to both be the same. What about 7? Is 7 continuous? That is not continuous either. Now, why not? Because the limits are not the same. The limit from the left-hand side, right, is 3. The limit from the right-hand side over here is negative 3. And as we know, 3 does not equal negative 3. Okay? They approach two different numbers. 3 is not equal to negative 3. What about problem number 8? Is that continuous? No, that is not continuous either. Why? Because the limit from the left is different than the limit from the right. The limit from the left is 2. So the right-sided limit is 0. 2 is not equal to 0, not continuous. All right? 1 from the negative side, negative 1 from the positive. Negative 1 from the negative, negative 1 from the positive. All right? All right. Try problems 9 through 12. Now this switches it up. Now you can discuss the continuity in the graph. So you're no longer going to say where the graph is discontinuous or not continuous. Now you're going to explain where the graph is continuous. So you're going to also use your intervals with the brackets and the parentheses as well to do so. So, ready? Problem number 9. First of all, we know there is an asymptote at negative 2. We know there's an asymptote at 2. Why? Because we could see the behavior going here, going to negative infinity, and infinity. So we're going to use that information to help us find out where it's continuous. So it's not continuous at negative 2 and 2 when x equals those two. So where is it continuous? From, this is negative infinity to negative 2, parentheses meaning not including, and then from negative 2 to 2, so parentheses means it doesn't include these two, and then from, 2 to infinity. Okay, so this pretty much means every number, but not negative 2 and not 2. If it was brackets, it would be included, but there's no brackets, so it's not included. All right, problem number 10. Oh, my little circle should be in front. All right, so let's look at this one. Whoop, let's fly over here. So it's continuous everywhere, but at this place right here where my hole is, and that hole happens to be at, the x value is negative 1. So not at negative 1. So it's going from negative infinity to negative 1, and from negative 1 to infinity. See, not too difficult, is it? Of course it's not. Let's go to the next one. Oh, this one has a bunch of stuff. So it's not an open interval, right? Because there's no arrows. But we start here. Now, because this is a closed circle, right? We use a bracket. So from negative 2. So right here, it's not continuous at any of these places. So not at negative 1, not at 0, and not at 1. Okay, it's also not continuous at 2, but we don't need to worry about that. And anything before negative 2 or anything after 2, including 2. So, way you would write this is included. This is a bracket because it is a closed circle. So bracket, negative 2 to negative 1. Now this is what gets most students every year. I do teach these things more than a year. So even though this is closed circle, you say, okay, is that bracket negative 1? No, this is still parenthesis, parenthesis. Okay, because you're saying at negative 1, it's never continuous. Okay, because these things don't connect. So now 0 is also parenthesis, from 0 to 1. From 1 to 2 is parenthesis. This is open to that. Now the only reason this is bracket is because you start here. Okay, so it is continuous there. Even though you end here, it's open circle, so that's why you have the parenthesis. All right, that's probably the hardest of the 4. Let's move on to number 12, which is an easy one. Not continuous at 1, right? That's the only place because there's a hole there. So from negative infinity to 1 and from 1 to infinity. See? Continuity 101. Got it? All right. Let's go on. One-sided limits and continuity on a closed interval. All right. So the limit of f of x as x approaches c from the negative side. That approaches from the, when you approach from the negative side, you approach from the left. So if this is c, I'm approaching it from the left. Limit of f of x equals the limit as x approaches c from the positive side, or positive infinity. So this is approaching from the right. That's when you're coming towards it. So c negative, c positive. And it's to those powers. Notice the negative and positive are not in front. That would just mean negative and positive values. This has nothing to do with the positive or negative value of the actual value. All right, so when c equals 1, c equals 1 is right here. What is the limit from the negative side? Now the negative side is from the left, so you're going to move down here, whoop, and right before you get here, the limit is 4. See from the positive side, this is the positive side, so you move down, 4. What's the actual limit? 4, right? What would be f of c? Really quick, bonus point. F of 1 would be 2. Is that continuous? Nope. All right, let's go 14. C is 2. So as you approach c from the negative, what's your answer? Good, negative 1. As you approach 2 from the positive, what's your answer? Positive 1. There you go. See the difference? Is there a limit here? Nope, the limit actually doesn't exist because the graph isn't continuous. Boom. Let's go up a level. Using one-sided limits to find the actual limits. Up. I was jumping up. All right, so if the two limits from the left side and the right side are equal, your limit is L, whatever the limit is. If they are not equal from the left and the right side, your limit, not undefined, D, N, E, or does not exist. Okay, so let's go to this one first. We said before the limit is 1 from the negative side. What did we say it was? We said it was 4. We said the limit of 1 from the positive side was also 4. Because they are equal to each other, the actual limit is 4. We already did this. This is just quick review. Okay, we're kind of like doing like a little circle. We're circling back. Circle back, circle back, circle back, like a little spiral. Make sure you guys get this. So, if the limits are not equal, f of 1, we said before was 2. I jumped the gun and gave you all the answers to this. Shoot. All right, so D and E, because they're not equal, so let's show you an example. As you're approaching 2 from the negative, answer we said was negative 1. As you approach 2 from the positive, your answer is positive 1. These things equal? No. So it's D and E or does not exist. Now, what is the actual f of 2 here? Because nothing's filled in, f of 2 is undefined. All right, that's it. I should have hopped over, but I didn't. Got it? Awesome. All right, next one. How do we use one-sided limits? This is the one I like the least, but I still teach it every year because it's in the book. So one-sided limits for radicals. This is a big portion of where you would use it. So as you approach 0 from the negative, the limit of 0 from the negative, does that equal the limit of 0 from the positive side? Now, 0 from the negative side, as you approach 0 from the negative, you can't do it. There is no answer. Even though 0, the root of 0, no matter what n is always going, as long as n is not negative, is always going to be 0, right? You can't approach it from the left because it's never going to be negative. Okay, so there's never an answer that's just before you get to 0. That's 0, but it's not 0. So that's when you would use the one-sided limit, the limit of 0 from the positive side, because there's a bunch of stuff here. And that would actually be your 0. See, now we're getting theoretical and hypothetical. We're a little crazy. So you can only find the limit, in this case, from the right-hand side. All right? Good. Find the limit of, let's do this one. Radical f minus x squared as x approaches negative 2 from the right. Left, right. What do you think the answer is? I'm sorry, and this is only when n is even. All right, if n is odd, obviously, you're going to have stuff from the left-hand side. So, as you approach from the left-hand side, right-hand side, your answer is, you can actually plug it right in. because we know there's a value here, right? You can actually plug 2 right in there. All right? You're going 2 and just a little bit extra, but you can actually plug 2 in there to see. When you square a negative number, it becomes positive. Or sorry, yep. So 4 minus a positive 4. 4 minus 4 is 0, and square root is 0, 0. All right? So the limit is 0. From the left, doesn't exist because you can't have anything from the left. Got it? All right. The existence of a limit. The limit of f of x equals L as x approaches negative x. The limit of f of x equals L as x approaches c from the positive. So this is from the positive, from the negative side. There's actually a limit if what is true about these two things. If they are equal. We're getting a little repetitive, but repetitive isn't bad because it helps reinforce the answers. So continuity on a closed interval. This graph right here, closed. Notice, closed circle, so it's from A to B. Okay, it's not just every single real number. So limit of f of x as x approaches A from the positive side is what? F of A. The limit of f of x as x approaches B from the positive side is f of B. Now, if these are open circles, it would not be a closed interval. So you could not do these things. Got it? And that's from A to B. You need to have closed circles on the ends of the limits. Got it? Or it's not continuous. If it's an open circle, f of A wouldn't equal the limit right there. Got it? Because f of A would technically be undefined. Now, this is a long problem. This was, I think, one of the last ones of the day. Discuss the continuity of f of x equals square root of 1 minus x squared. So let's find out first on the closed interval what the domain is. So how do we find the domain here? What do we know about radicals? The answers inside radicals have to be what type of numbers? They have to be positive numbers. They also could be 0. So they have to be greater than or equal to 0. Okay? So when you have f of x equaling this inside part can't be negative. Okay? So it can't be less than 0. So therefore it has to be greater than or equal to 0. What I just said. So you solve for x squared here. You minus 1 from both sides, or you add x squared to both sides, okay? And then you would divide by negative 1. You just end up with x squared is less than or equal to 1. I'm just going to reverse the order, just because that's typically how you write it. You put the variable first. All right, so that means that x can be anything bigger than or equal to negative 1. That's my domain. That's any number I can plug in there. Is that always true? No. It's also x has to be less than or equal to 1. Because I'm doing a square root right here, okay? Now, because negative 1 squared is 1, that's why it's less than or equal to, and then I could also say 1 squared is 1. So it's pretty much your answer is going to be greater than or equal to negative 1 and union with less than or equal to 1. So it's going to be between negative 1 and 1, and you can see it shown right here in the graph. When you write this as bracket, negative 1, including negative 1, comma, all the way to 1, bracket. So it includes both. All right? Check for continuity. Now, the way you would check for continuity of something, we're not going to do problems like this in tests or anything, but just always good to know. You would just got to make sure your limit at negative 1 from the positive side is equal to your actual f of negative 1, and your limit as you approach 1 from the negative side is equal to the actual value there. So when we take this limit, you can just take your negative 1, whoops, sorry, and this just means from negative 1 to 1. That's my MIP. So I'm going to take a number that's just a little bit more than negative 0.1. So if I take negative 1 and I add a little bit to it, say I add a thousandth to it, you get negative 999 thousandths. All right, I'm plugging it in there. I get about square root of 0.002, which is about 0. It's 0.000 and some numbers. We'll round it to 0. If I actually take negative 1 and plug it in here, negative 1 squared is 1, and 1 minus 1 is 0. Square root of 0 is 0. All right? Are these equal? They are equal. Since they are equal, that means it is continuous at this point. Okay, the graph really wouldn't be given to you. I'm just using the graph to show you what we're talking about. Take a number, now you're going from 1, a little bit less than 1. So take 1 and subtract the thousandth from it. All right? So as we approach here, that right there, we're good. 0.999 squared, 999 thousandths. 0.002, square root of that is 0. Okay, take 1, plug it into the equation. All right, as you plug it into the equation, 1 minus 1 is 0, square root of 0 is 0. What do you notice about these two? The limit of f from the negative 1, all right, as you approach this from the negative side, is actually equal to the actual value there, so therefore it is continuous. All right, not too terrible, is it? A little tedious, so yes, continuous. Domain, continuous. All right, that was a little wordy. All right, take a breath. All right, so next one, do now. Answer the 3 following questions. 1, where is the following graph not continuous? Where? X equals 1. Number 2, find 0 from the negative. So, oh, it's there because it's a whole. 0 from the negative, I approach 0 from the negative side. Negative 1, negative 2. 0 from the positive side. 2. All right. What's the actual limit there? These two things are not equal to each other from the left and the right, therefore, it does not exist. What is actually f of 0? What's the actual, where's their closed hole there? There is none, so it's undefined. That's not too terrible, right? 0 from the negative. Now, this is what we're going to be covering in a little bit. 0 from the negative. Your graph's actually going to be shooting up, 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 up in the air forever into negative, a positive infinity. 0 from the positive. It actually shoots up in the air forever to positive infinity. Because this is unbounded behavior, the limit doesn't exist. Right? F of 0, what's the actual value at 0? There's an asymptote there, so it's undefined. These f of x's can be undefined. The limits are non-existent. These 3 problems look familiar? They should. That's how we started the whole chapter. When I introduced limits to you, I said, this is what limits look like. No? All right. Hopefully, maybe you remember. All right, so now we're going to get out of the graphs, and we're going to go up a level. Now we're going to do this analytically. Okay, we're going to do this just with equations. So, find if the limit exists. If not, explain why. Now, we're doing this one-sided. All right? So, let me explain something to you. When you have 8 plus, that means it's just a tad higher than 8. So, pick a number a little bit bigger than 8 and plug it in there. What's a number a little bit bigger than 8? Not 9, that's too much bigger, just a little bit bigger. How about 8 point, a bunch of zeros and a 1? Do you have to go that crazy? No. Easy for me just to hit the 0 button and leave my hand on it and make sure it fits. All right, so that's technically what you're going to do, but there's an infinite more number of zeros between there. All right? So if I type that in there, what would be a number similar to 8 I could put in? Or similar to that? 8, right? So if I just typed in 8, I just round this to 8, 1 over 8 plus 8, I get 1 over 16. So there's my limit. All right, the one-sided limit happens to be the same on both sides. So if you could just type in this number in here and get an answer, you're set. There's no other work to do. All right, now what about this one? A number a little bit less than 5 is 4 and a bunch of, pretty much a 9 with a line over. Now instead of typing that in your calculator, your hand's going to get bored 9 so many times, just type in 5. Negative 3 over 5 plus 5, 5 plus 5, oh, I can solve that as 10. Negative 3/10 is my answer. All right, so you can solve these as one-sided limits, if you can. If you can't, I'll show you what to do next. Now, look at problem 21. All right, so say 5 and a bunch of zeros and a 1. The only reason this is shorter is I couldn't fit the other stuff. Now, if I type my 5 in here, 5 minus 5 is 0. 5 squared is 25. Oh, minus 25 is 0. 0 is undefined. Oh, darn it. Now what do we do? Anyone have an idea? Think back to regular limits. I heard you. What did you say? Say a little louder. That's right. If you factor it, maybe we can cancel stuff out. Can you factor x minus 5? No. But remember how to factor x squared minus 25? Perfect square. X plus 5x minus 5. Now, can we cancel anything out here? Yes, we can cancel on x minus 5 on the numerator and denominator, leaving the numerator as a 1. Okay, remember, this has to become a 1 up top. 1 divided by x plus 5. Now, what do we do after we do that? We plug back in our 5 again. 1 over 5 plus 5. 5 plus 5 is 10. Your answer is 1/10. So just as we did with regular two-sided limits. All right, plug in the number. If you can't do that, factor it, plug it in again. If you can't do that, now we're in trouble. All right, so let's look at problem 22. A little bit more than 2 is 2 and a bunch of zeros and 1. And let's just plug in 2. Ah, man, it got undefined. Can we factor the top? Not really. Can we factor the bottom? Yeah. If we factor the bottom, we get x minus 2, x plus 2. X minus 2 and x plus 2 don't match this. You get negative x plus 2. But if I want to switch the signs, remember, you could pull out a negative 1. That makes this become positive, your x, and the 2 become negative. And now look what happens. This is still the same as this. What can I do with these two guys? Bye-bye. Cancel out. Left with negative 1 over x plus 2. What's the next step? Plug in my 2. Negative 1 over 2 plus 2 is negative 1/4. All right? We all good? Awesome. All right. Problem 23. 23, as you can see, being that there's a table down there, something's going to happen. Let's plug in our negative 3. Plug in our negative 3, we end up undefined. I can factor the bottom, x plus 3, x minus 3. But guess what? I can't cancel anything. I plug in my negative 3 again, I end up with undefined. Because it becomes negative 3, 0 times negative 6, negative 3 over 0, which is undefined. All right, now what do I have to do? I have to make my table. I'm approaching negative 3 from the left-hand side, right? So that means I'm going to look at all the numbers leading up to negative 3. Now, do you remember when we went back all the way to, what was it, 2.2? When we did the tables? Now you only have to do half the tables. If it's from the negative side, you do the left-hand side. If it's positive side, you do the right-hand side. Pick a number. I'm going to pick 1,000. Type that in. Negative 3.001 divided by open parentheses, negative 3.001, close parentheses squared, minus 9, close parentheses. Notice I had a set of parentheses for both the whole denominator and this number that I was squaring. So I had 2 there. I get about negative 500. All right, that's a weird number. So let's pick a number a little bit less than that, negative 3.01. All right, type that in the calculator, you get negative 50. Now you can pick negative 3 1/10 if you want. In this case, I go, you know what? I really want to show you why this is doing what it's doing. So as you can see, it's jumping up by a unit of 10. Say I pick 3, and you don't have to pick this number. I'm just showing you 3 and a bunch of zeros and a 1. I type that in there, I get negative 500,000. So now you could really see negative 50, negative 500, negative 500,000. What is this jumping up to? It's going negative 50, negative 500, negative 500,000. It's off the screen. And then if I add more, negative 5 million, negative 50 million, negative 50 billion, 5 trillion, stuff like that. So this, as you're getting closer and closer to negative 1, what's your graph doing? It's going more and more towards negative infinity. All right, so one-sided limits at times, if you start seeing these jumps, are going to go towards negative infinity or positive infinity. Let's check out problem 24. Not going to need a table for this one. All right, so multiply by the conjugate. You thought that was over, didn't you? So conjugate is you take this number, you just add a plus to it. This becomes x. All right, 3 radical x minus 3 radical x. The middles cancel out. Minus 9. All right, so you still have your negative out front. X minus 9, x minus 9. They cancel out, leaving you with a 1 in the numerator. Negative 1 over radical x plus 3. Let me put my 9 in there now. And even though it's a number a little bit less than 9, like 8.9 repeating, we'll just throw that 9 in there. Radical 9 is 3. Negative 1 over 3 plus 3, negative 1 over 6. All right? If this was a positive, it would probably go towards infinity or negative infinity. I really don't know off the top of my head. Got it? But in that case, you got that. All right? Let's move on. All right. To make sure you guys understand how to do this stuff and are capable of it, we're just going to set up charts for different values of C. All right? So the first chart says x is approaching 4 from the negative. So since it's approaching 4 from the negative, am I going to get all the numbers leading up to 4 or all the numbers a little slightly after 4? From the negative is, you should say, all the numbers from the left leading up to 4. So if I put 4 over here, right? What's the number? We're just going to subtract 1,000. So that would be what? 3.999. we're going to subtract a 100th, which would be 3 99/100th, and we're going to subtract a 10th, 3.9. So why don't you try that for the rest of these? Do the 1000th, 100th, 10th. If you want to do different units, you can, just as long as you do them in ascending or descending order. All right, -3 from the positive side. From the positive side, you're coming from the right. So you're going to end up with -3 over here. So you're going to add 1,000th, which is actually -2 999,000. Add 100th, which is -2 99/100. And add a 10th, which is -2.9. Right? Got it? Finish. Did you finish? You really finished? Good. 6 from the positive means you're coming from the right. So you're going to add 1,000th, add 100th, add a 10th. 6 and 1,000, 6 and 100, 6 and 10. And then you just take each one of these numbers, plug them into the original equation, and then it'll tell you if it's going towards infinity or negative infinity. That's what they're going to have to go towards. If you don't, for one-sided limits, it's not going to be does not exist. It could be infinity or negative infinity. All right, for these, from the left to -8, so you're going to subtract 1,000, subtract 100, subtract a 10. All right. 0 from the negative. That means you're coming from the left, approaching 0. So -1,000, -100th, -10th. It's actually that. From the positive, you come from the right, and you have a 0 here. So you add 1,000, add 100, add 10th. That's it. Hopefully this helped you with your chart setting up skills. If it didn't, practice some more on your own. Come show me your answers. I'll tell you if you're good or bad. All right. Let's move on. Halfway point. Yay. We're almost halfway through the lesson at 35 minutes. That's not too bad. All right. Did you solve the do now yet? Make sure it's on Canvas. Factor. You plug in 6, undefined. See, I already knew you had a factor. Variable squared. X minus 6, x plus 6. So, remember, x squared minus a squared equals x minus a, x plus a. X minus 6 over x minus 6, x plus 6. X minus 6's cancel out, leaving with a 1 in the numerator. 1 over x plus 6. Now, you plug in a 6 here, not a -6. This is a number slightly less than 6, like 5.9 repeating. So we'll just plug in 6, we'll estimate. 1 over 6 plus 6 is 1/12. And guess what? 6 from the positive would also be 1/12. Let's do this one. Plug in 1. Undefined is an answer. All right? Undefined, so we factor it. X minus 1, x plus 1. Cancels the x minus 1's out, leaving with the 1 in the numerator. 1 over x plus 1. 1 plus 1 on the bottom. 1/2. We all good? All right, C. Cancel out the x's, right? Oops, undefined. So do we cancel out the x's? No, you cannot cancel out the x's. Unless this 5 has an x next to it, you cannot do that. So we cannot factor this. What do we have to do? Make the table. Now, 0 from the negative means we're coming to 0 from this direction, right? So we're going to end up at 0 here. So we subtract 1,000. So we end up at 0. Subtract 1,000. Subtract the 100th. You really only have to make 2 of them to see what you're going towards. So let's plug in something. Let's plug in 1,000. Let's plug in 100. In parentheses, 5 minus -0.01, close parentheses, divided by -0.01. -501. Parentheses open, 5 minus -0.001, close parentheses, divided by -0.001. I'm going to guess 5,001, -5. Ooh, see the jump? -500, -5,000, -50,000, 500,000, 5 million, all the way to negative infinity. See that? Ha! And you thought this was going to be hard, didn't you? All right, let's go to the next one. All right, can't factor the top. X plus radical 3, x minus radical 3 doesn't do us no good, and that's not even a negative sign. So the answer here is negative. So -19 over 0 is undefined, can't factor it, so you make the table. 4 from the positive side means we're coming from the, where I was just sitting to the right. So we're going to add 1,000, add 100. So when I add 100, open parentheses, 4.01 squared plus 3, close parentheses, divided by open parentheses, 4.01 divided by 4, close parentheses, you get 1908. 4.001, you get 19,008. Then you get probably 190,008, 1.9 million and 8. And where our graph doing is going up into positive infinity. Good. Awesome. All right, one-sided limits. Here are the rules. And if you follow these rules every time, this will indeed be easy. Rule number 1, you just plug in whatever the C is. If it's coming from the positive side or the negative side, you just plug in C. If you get an answer, you're done. So if you get an answer, done, that's your answer. If you don't get an answer, you get undefined as an answer. Unfortunately, you go to step 2. You factor or reduce, or you multiply by the conjugate. Do one of those things. After you do that, you plug C back in again, and you get one of two things. You can either get your answer and be done, or you get undefined. If you get undefined, make a table. So when you make a table, when you have C from the positive side, that's number slightly more than C. You add 1,000 to add 100. If you have C from the negative, that's slightly less than C. You subtract 1,000, subtract 100. So, and that will give you one of two answers. That's either going to give you a negative infinity or a positive infinity as an answer. When you do a one-sided limit, you have to have an answer. All right? Unless it's a part of a graph where nothing exists. All right? And I don't see you getting any of this stuff. Got it? Got it? Good. Limit for one-sided limits is never D. In this case, in my class. And there's always exceptions to the rule, but we're not going to deal with that. All right, so properties of continuity. B is something called a real number. You know what a real number is? Any number. F and G, you know what those are? Functions. And they are also functions that are continuous at x equals c. Now, there are 3 plus 1, which is 4 rules that you can use with your properties. The first one is called scalar multiplication. Now that's when you take a real number and you multiply it by your function. For instance, if your function was x, you could do 3x, 4x, 1/3 x, 1/8 x, square root of 48x, stuff like that. So an example we can use is 5x cubed, right? X cubed would be our function that's continuous. And if you multiply by any number, it's still continuous. Second thing is a sum or a difference. So that's when you take 2 functions and you add or subtract them. That will still be continuous. Okay, if both these functions are continuous, by adding 2 continuous functions, you still have a continuous answer. So for instance, if I take x to the 5th and I subtract 1 over 1 plus x to the 6th, which is always going to be continuous, right? Continuous. Product. Multiplying 2 continuous functions gives you a continuous function. So say I take 6x to the 3rd times cosine x. Guess what? Continuous. Quotient, when you divide two functions, as long as your second function never equals 0, otherwise it would be undefined, then you're good. So x to the 7th, x to the 4th plus 10, this bottom piece can never equal 0. Therefore, this will always be a continuous function. Right? And those are your properties. Let's check this out. This is an easy one. Before we do that, there are 3 plus 1, which is 4, types of functions that can be continuous. First one is a polynomial. A to the n, x plus 1. These things in the front, they're just constants. And then this is just your increasing or decreasing, raising your extra variables. So what that means is, say you have a polynomial, doesn't matter what your lead degree is, typically continuous. Any polynomial, always going to be continuous. Everywhere. Alright? Got it? If it's a straight polynomial. Got it? Awesome. Rational. If you have 2 functions divisible by each other and the function on bottom can't equal 0, it'll always be continuous. So, for instance, r of x is this over the bottom piece. The bottom piece here is never going to equal 0. Hopefully. Well, this is continuous except for where this bottom piece equals 0. Fortunately, I picked a problem where, because this is a negative, it can't equal 0. Stupid me. Alright, I'm going to change that to a -5 and be better. Yeah. All right, radical. If n is even, x cannot be negative. So therefore, it's continuous everywhere greater than or equal to 0. If n is odd, it's continuous everywhere. Even, only when this is positive, or 0. Odd is continuous everywhere. Got it? Trigonometric, sine, cosine, tangent. Cosecant, secant, cotangent. These, sine, cosine, continuous everywhere, okay? So no matter what you do to a sine or cosine, it's always going to be continuous. Tangent, cosecant, secant, cotangent, all have asymptotes. So they're continuous in a lot of places, just not where the asymptotes are, right? And the asymptotes can shift or move depending on periods and horizontal shifts. But sine, cosine, always continuous. So let's go look at this now. Are the functions continuous at every point? Do you problem? So first one, what do you think? You should have said, so let's look at this. I'll just do these graphs to show you. The graph of x, all right, identity graph, wherever x is, y is. That's continuous at every point. Sine x, continuous at every point. So since they're both continuous at every point due to the sum theorem, yes, it is continuous at every point. What about 32? X and sine are continuous. What are these green guys? Asymptotes. So the answer is no. These graphs is not continuous at any place this is green, and because it's undefined at all these green spaces. Also, the limits don't match from the left and the right side of those green. Now that's n pi over 2. What exactly does n pi over 2 mean? Is when you have a tangent curve, every pi over 2 times any n has to be an integer. Okay, that's any negative, positive, like whole number, kind of, and 0. So if I multiply those all by that, at all those places, there are asymptotes, not continuous at any of those. Problem 33. Is it continuous at every point? This is a tough one. Well, x squared plus 1, continuous at every point, good. Cosine x, continuous at every point. So the answer should be no. Wait, that doesn't follow the rule, does it? But actually it does. Why is the answer no? Even though x squared plus 1 and cosine x are both continuous, cosine x equals 0 at n pi over 2. See all these dots? Every pi over 2 times a number, the graph passes through 0. Anytime cosine x equals 0, anything divided by 0 is undefined. So then it would not be continuous. Okay? Got it? All right, why don't you guys try 34 and 35. All right, 34. X, e to the x. X, always continuous. E to the x, always continuous. Is it always continuous? Yes, when you add them together, they are continuous. Oh, this is a tough one. X squared, is that always continuous? Yes. Is cosine x always continuous? Yes. Does it matter that it passes through zeros all this time now? No, because that's a numerator. Numerators can be 0. X squared plus 1, is that continuous? Yes. Is x squared plus 1 ever going to be 0? No. All right. So what does that mean? Yes, it is continuous. Awesome. Ready for the next one? Problem 36, 37, 38. Go, go, and go. All right. Tan x on the interval. So negative 3/2 pi, negative pi over 2, and 3 over 2 pi. What are all those? Those are all asymptotes. What happens at asymptotes? Graphs are not continuous. So this graph is continuous. All right? From negative 3 over 2 pi, pi over 2, parenthesis, negative pi over 2 to pi over 2, parenthesis, pi over 2 to 3 pi over 2. All right. It's also this little piece, but we don't know where that ends. We don't know that begins, so I just keep that. Oh, it said on this interval. So that's your start point, and that's your end point. 37. Where is that graph continuous? Well, where is it not continuous? When the denominator is equal to 0, right? X minus 1 can't be 0, the graph is undefined. So when x can't be 1. So since it can't be 1, it could be everything from negative infinity to 1 and from 1 to infinity. 37 actually became an easy question. When 1 is 0, this graph is not continuous. When is the denominator 0? Can you factor that? Factors of 8 that add up to 6, 4, and 2. X plus 4, x plus 2. X plus 4 can't equal 0, so subtract 4 from both sides, x cannot equal negative 4. X plus 2 can't equal 0, subtract 2 from both sides, x can't equal negative 2. So negative 4 comes before negative 2 from left to right. So you got negative infinity to negative 4, negative 4, 2, negative 2, and negative 2, 2. Got it? Awesome. Oh, man, Mindy. All right, describe where the function is continuous. What do you got? Look at the graphs. Everywhere, right? From negative infinity to infinity, or you could say the R with the double right-hand side, all real numbers. What about this one? From here, whoop, all the way to there. This is negative 3 because it's a closed circle. Use a bracket. Negative 3 to infinity. Right? What about C? Negative 2 and 2 are asymptotes, right? So from negative infinity to negative 2, from negative 2 to 2, and from 2 to infinity. And D. Well, there's going to be an asymptote right here at 0. And this graph does go to positive infinity, so you're going to go 0 with a parenthesis all the way to infinity. Good? Awesome, awesome, awesome. And just if you want to check this stuff, this bottom's never going to be 0. This one you would say x plus 3 has to be greater than or equal to 0. Let's figure out that. This one, secants have the asymptotes. And this thing right here, x has to be greater than, or x cannot be 0, and it can't be negative, right? Because of that stuff. Because you can have a negative under a radical. So x has to be greater than or equal to 0. All right, go this one. We're just going to touch on the IVT. Intermediate value theorem. If f is continuous on a closed interval a, b, so from A to B, closed because there's closed circles, boom, ba-doom. All right, and K is, what is K compared to A and B? F of A and F of B. Between, it's between the two. There is at least one number C, all right, in A, B that F of C equals, what do you think? K. F of A cannot equal F of B. So all this says is, if you take a thing, if you take a interval, right? You take a number between that interval. There is going to be numbers that when I plug in the A, I plug in the B, I get two numbers. This C, there has to be a number somewhere in here that's between these two numbers. And what you do is you pretty much keep on squeezing that number till you actually find out what K is. Now in this case right here, this is no good. Why? Why is there no K here? Because this graph is not continuous. This is continuous. This is not continuous. Got it? Simple concept. I think I dumbed it down too much, but it took longer to make than it did to explain. All right, so next one. Tell where these graphs are not continuous. We're going back to domain and range from the pre-calc. Told you we'd come back. The denominator cannot equal 0, right? 6 divided by 0. X cannot equal 0. So it's not continuous when x equals 0. When's a polynomial not continuous? It's always continuous. Isn't it great to get easy problems once in a while? Polynomial. always continuous. Denominator can't be 0. So x minus 2, when that is equal to 0, it is not continuous. So when add 2 to both sides, when x equals 2, the graph is not continuous. All right? I know this seems easy, but it's always good just to throw some easy ones back in some easy ones. All right, find the values here. Fraction, so when that denominator equals what? It's not continuous. When the number divided by 0 is undefined, so when that's 0, I'm going to add x squared to both sides. Square root of 4. What number squared equals 4? Not just 2, but a positive or negative 2. All right, and there'd be asymptotes. When x plus 1 equals 0, so I subtract 1. When does x squared ever equal negative 1? But we're not dealing with imaginary numbers in this calculus. Always continuous. Yes. What about here? 3x is continuous at all times, right? Cosine x is continuous at all times. Subtracting two continuous numbers, you get a always continuous. 46. Cosine x is always continuous. So cosine, whatever's inside is always continuous. So your answer is always continuous. All right. 47. Which value is not continuous? Oh, no. All right, now, any number divided by 0. So, x squared minus x. When that equals 0, your graph is not continuous. You don't want to factor first. Factoring helps you find limits, but it actually messes up your answer if you're dealing with continuity. So I'm going to pull an x out. X times x minus 1 equals 0. I'm going to set these both equal to 0. X equals 0, x minus 1 equals 0. Okay? X equals 0 and x equals 1. That's when it's not continuous. Next problem. When x squared minus 1 equals 0, your graph is not continuous. Can I factor that? X plus 1, x minus 1, right? Or I could just say, add a 1 to both sides, x squared equals 1, x equals plus or minus 1. Factored either way. All right, 49/50. When is f not continuous? I could trim this down and use less paper probably, but everyone always complains I don't give enough space. When a number divided by 0 is undefined, so when x squared plus 1 equals 0, x squared equals negative 1. When does x squared ever equal negative 1? Never. Always continuous. X squared minus 36 equals 0. I know I can make this x plus 6, x minus 6, and I can cancel out the x minus 6, but it's still not continuous at that point. It just means there's going to be a hole at that point. So I add 36 to both sides. X squared equals 36. Square root what two numbers squared are 36? X equals a plus 6 or a minus 6. Ready for the last question of the day? Problem number 51 and 52. Not continuous. Set both denominators equal to 0. X squared minus 3x minus 10 equals 0. What are the factors of negative 10 that add up to negative 3 when you subtract them? Negative 5 and 2. X minus 5, x plus 2. X minus 5 equals 0. X equals 5. X plus 2 equals 0. X equals negative 2. Negative 2 and 5 are the two values where x is not continuous. 52. X plus squared plus x minus 2. Two values of these you subtract to get 1. 2 minus 1. X minus 1. X plus 2. X minus 1 equals 0. X plus 2 equals 0. X equals 1. And x equals negative 2. Negative 2 and 1 are the two values of x where f is not continuous. That's where there's going to be breaks. In this case, asymptotes. Nope. X minus 1 will be a whole. X plus 2 will be an asymptote. We'll get into that right later on. If you factored this first and you canceled out the x minus 1s, what I'm talking about that you may not understand, because they cancel out, leaving you with 1 over x plus 2, there's still a hole there, okay? Because the limit's the same there from both sides, but there is a hole there still, so it's still not continuous. And then the x plus 2, where x equals negative 2, that would be an asymptote, all right? We'll get into that later on. We'll jump a lesson. And there you go, continuity and one-sided limits. So, congratulations on learning a little bit more about limits. There's only one more quick lesson on this, limits of n behavior. a little more graphing, and then we're pretty much done with limits, and we can get into the good calculus, which is derivatives. So, till next time, have a good day.